Yep. I'm starting the recording. So someone in class answered the question correctly. So keep in mind, upcoming quiz. If I ask you to classify an alcohol, can you identify if it's primary, secondary, tertiary, but also allylic and benzylic? Or if you need to, please make sure that you have that type of knowledge down. The only aromatic, which is a phenol, and I don't really classify that as an alcohol, but sure, you should know what a phenol group is. Allylic and benzylic. So allylic is when you one away from a pi bond, and benzylic is when you one away from a phenylene. All right, so make sure you guys have that down from alcohols first. Can I classify them? Second thing is, can I name alcohols? All right, so you guys have known the processes for naming alcohols. What are the processes for naming alcohols? Identify the longest chain, right? Number the chain, deal with substituents, and then name the molecule, right? If an alcohol is the main functional group, what's the ending? Oh, well, that's right. It should be all. If the alcohol is not the main functional group, how do we identify the alcohol? What word do we use? Anyone in teams?
Was it phenol?
Say that again?
Phenol?
Not phenol. Keep trying. Yep, hydroxyl is what I'm looking for. I don't know if that's. And hydroxyl is what I'm looking for. All right. So when the alcohol is not the parent, we have to classify it as a hydroxyl group, right? So you might hear words like 4-hydroxyl pentanol or 4-hydroxyl penoic acid, all right? Because the carboxylic acid will have higher priority. So keep that in mind. All right. The next thing outside of naming and dealing with the classification of alcohols is to talk a little bit about its physical properties and what physical or what intermolecular forces are present in alcohols again. So you guys have in your notes, hopefully, that all three intermolecular forces are present, right? I have van der Waals or London forces. I have hydrogen bonding with also dipole-dipole interactions, right? So that makes alcohols have high or low boiling points. Yeah. So alcohols would traditionally have higher boiling points than normal, right? Because hydrogen bonding is so strong, right? It takes a lot of heat to break those up, all right? So everybody's comfortable with that. Now, when we think of solubility, we have to think about its interaction with a particular solvent. Typically, we're going to probably be thinking about water. So can alcohols dissolve in water? Yeah, yeah. For the most part, most alcohols can if they're not longer than 6 carbons, all right? Longer than 6 carbons that have a little trouble dissolving in water. Very good, all right? And the next thing that's here is our classes of reactions. Do you guys remember what type of reactions can alcohols undergo? Anyone? Dehydration. All right, dehydration is one. Oxidation is one. Good. Substitution is one. Okay, they could be reduced. Esterification and tosylation. All right. So I'm going to summarize esterification, tosylation as reactions of O. And there should be also etherization. You're going to etherize these compounds. The Williamson ether process. All right, very good. So those will be reactions at O. We're going to cover those today. Oxidation is a unique class of its own. We'll talk about that as well today. And obviously, you guys have some clue on dehydration reactions. All right, so very shortly here, we'll get into these reactions. All right, I was hoping that my computer would be up by now. All right, while we're waiting on my computer to finish, tell me something about elimination reactions. What do you guys know about elimination reactions? So somebody says E1 or E2. Which one is it? Is it both? Yeah. Somebody said yeah, it's both. Okay. Somebody said E1.
E1.
What's the question again?
Yeah. Tell me what you know about dehydrations.
Oh, they're E1.
They're E1. Two steps.
Leaving group leaves first.
Okay. Tell me the steps of the mechanism. So I need to form what before my leaving of leaves?
Carbon cation.
Yeah, I need to protonate the OH group, right? That forms the water molecule that leaves to generate the carbon cation that can then I can do my elimination process, right? Very good. Very, very good. Carbon cations, we have an issue with those. What's the issue with carbon cations?
They have rearrangements.
Yeah, rearrangements. All right. I haven't done any examples with rearrangements yet, but you guys want to keep it in the back of your mind that carbon cation rearrangements can occur. All right. That means that the products will change based off those features. All right. I will have a worksheet where you guys will be working with those. You want to make sure that you're looking for potential rearrangements. Okay. Good. I'm almost there. Come on, come on, come on, come on.
Dr. Cooper, are you saying something?
No, no. Sorry.
Okay.
No, my computer is completely frozen. Just give me a few more seconds. I'm hoping that I can get this to work here. Good morning. Good morning, Ms. Page. All right. Be All right, can you guys still hear me? I just switched over to the main computer here. Sounds like a yes. I hear myself in class. All right, I'm almost there. Almost there. All right, can you guys give me a show of hands if you can see my screen? Okay, I see a few hands. Is there anyone that has a mic that's not seeing my screen? Can you let me know? It looks like everyone is cool. All right, let's go ahead and summarize really quickly our reactions to alcohols. All right, and we need to finish this on Thursday. All right, I'm gonna make sure that I'm here super early because it looks like every day I try to come my normal time. Something's coming up. Let's go 44 on that. Let's go bold. All right. The first class of reactions to alcohols are dehydrations. All right, you guys know step one right now. There's two ways of doing this. All right, part A is just an acid heat. All right. We're gonna come back and talk about part B shortly. I want to introduce a different idea before we come to part B. All right. Obviously, there's another way to dehydrate that's base related. Okay. Actually, maybe I should just go ahead and give it to you guys. All right. Part B is with, actually, it's not, it doesn't have to be. It's POX3 with trialpha amine. Okay. I'm going to color this in blue. So the first conditions are your acid conditions. I can dehydrate any alcohol with acid and heat. And my second conditions are a base condition, all right? So if I want to put my words here, I'm going to say this is the way to do this with acid. And this is the way to do this with base, okay? Why do you think that's important?
One does elimination.
Okay, they both are going to eliminate. So they both are going to form an alkene. So maybe I should put this here.
Dr. Cooper, Raylan says she can't see the screen.
Okay, somebody cannot see the screen. All right, give me
Yes,
one.
sir.
Let me see if I can reshare this really quickly. All right. All right, I'm going to stop sharing. All right, I'm going to open the share tray. All right, can you guys see now? Yes, no?
Yes.
Okay,
Yes.
good. All right, so both dehydration types forms alkenes. All right, they're going to be double bond forms. However, there are some substrates that are sensitive to acid. So if I wanted to dehydrate, I can't use acid. So instead, I use which version you think? I use the base version, right? And there's some compounds that are sensitive to base, so I use which version you think? The acid version, all right? The acid version is the most common, all right? So just taking alcohol with acid and heat, most people do it that way. All right, the second version is kind of a specialty thing. You have to really be sensitive to acid. There's something on the compound that acid can't see, and then you want to do this a different way. Let's talk about the mechanism types here, and we're going to give some examples. All right, part A, when I do acid and heat, is only going a E1 mechanism. So that means I need to be aware of what here? Rearrangements, right? All right, let's see if I can make that a little bit smaller. All right. Part 2, however, is undergoing a E2 mechanism. So do I concern myself with rearrangements here? This is no rearrangements when you do it this way, right? So you can see another advantage of the second reagents. What's that second advantage? I can do a dehydration without what? Without rearrangements, right? So sometimes you want to do things without rearrangements. So let's take a look at a couple of examples really quickly. I'm going to take this alcohol. Sorry, I haven't finished it yet. Give me one sec. Let me change my settings on this. Okay, I'm gonna start with this compound. Can you guys see? Teens, you guys are still with me, right?
Yeah.
Okay.
Yes, sir.
All right, good. I'm gonna use H2SO4, and I'm gonna use down here my delta symbol. Right. Some random people calling me. All right, I'm gonna do the same thing. And is everybody comfortable when I use the word X up here? That's just saying halogen. So maybe I should put this in green. That's any halogen, anything in group 17, right? Fluorine, bromine, etc. All right. Most people like to use the chlorine or the bromine version. All right. I want to know the products here. Can I predict the products of each one of these? All right, any takers? So if I do this the normal way, this is my acid conditions, right? And I might not have time to do the mechanism today, but we will cover the mechanism of all these. You want to internally think about this mechanism if you can. All right, I'm going to protonate this, right? That's going to be HO, it's going to be H2O or H2O. It's going to be water eventually once it gets protonated, and it's going to leave the form of carbon cation, right? Can that carbon cation rearrange? It can. Very, very good. So hopefully you guys are seeing this mentally at this point. I'm going to draw the carbon cation that you should be able to see first. I'm going to get this carbon cation from the first steps of the mechanism. All right, what I'm doing here is not the mechanism. This is just, oh boy, I think I'm going to confuse myself now. This is kind of just thinking about what happens, all right? In this case here, this carbon cation is secondary. Can it rearrange to something better? More stable than secondary? So this one can, right? I can do a,
A methyl shift.
that's right.
Dr. Cooper,
Yep. Go ahead.
when you draw that arrow going down underneath the actual yield arrow, are
Uh-huh.
you showing predictions?
No, this is like an abbreviated mechanism. So I'm not showing all the curved arrows. I'm just showing that this gets protonated and leave, and I form this intermediate.
Okay.
Good question. I'm just trying to show parts of the mechanism. So hopefully you guys saw that this has a methyl shift. I'm going to minimize this. All right. So what is my final product going to be then if I do all this? Hope you guys can recognize that my final product, yep, should be this. Very, very good. That's not going to look any better. I'm going to not do it that way. Okay, any questions there? Yep, I didn't do the full mechanism, but internally, you guys should recognize that this OH group gets protonated. It's going to form an HOH plus, right? All right, so I'm just protonating the O. The oxygen has to get an extra H. It's going to put a formal plus charge in the oxygen. That's a great leaving group. That's going to be water formed here. That's going to leave as water to form that carbon cation. Right? So I kick off water, I get a carbon cation here. Every time I form a carbon cation, I have to stop and think, can it rearrange? This starts off secondary, but if I do a methyl shift, I go from something that's secondary to something that's what now? It's tertiary.
Tertiary.
Yep. So I go from secondary to tertiary. So that's productive, right? Carbon cations want to rearrange to be more stable. Right? That's just the way it works. Anytime they form a solution, they're going to always do a quick rearrangement to get as stable as possible. So this will go from secondary to tertiary. And once it does this rearrangement, now I can finalize my final product. So I had to think about, in E2 processes, I have to pull from the side that has the fewest hydrogens, right? So if I look over here, there's 3 hydrogens here, there's 2 hydrogens here, but there's 1 hydrogen there. So I'm going to pull that 1 hydrogen there to form this product. And that's also known as which product from E1 mechanism. It starts with a Z. I'm sorry, a Z. So that's why I said the whole word. It starts with a Z. This is the zeta product, right? What is the zeta product? It's the more stable alkene, right? That forms from elimination. And the more stable alkene means what? More substituted, right? So tetra-substituted alkenes are more stable than tri, which are more stable than di, which are more stable than mono-substituted alkene. So if you need to, make some notes there to go back and revisit that, all right? But you should recognize that this is going to form the most stable alkene it can, because it's going to pull the proton from the side that has the fewest hydrogens. Okay, very good.
Dr. Cooper.
Yes,
So
ma'am.
anytime you do a methyl shift, is it you gonna form a double bond?
No, not necessarily, but if it's an elimination, it's going to form a double bond. You could do a methyl shift and then have a substitution happen, right?
Yes, sir.
Yeah, but in this case here, these are eliminations. So whenever you're doing an elimination process, that's what happens.
Yes, sir.
Yeah, so you know it's a substitution. It depends on the reagent, right? The reagent tells you what happened. The only thing acid can do to a alcohol is it's protonated, right? And kick off water. And so when that happens, the only thing left to stabilize itself is just to form an alkene. There's nothing else that can substitute in, right? There's no nucleophile that can come in, right? Because we didn't introduce a nucleophile. We're going to show that you can substitute alcohols, but you have to bring in a nucleophile to do that. Okay, good. Down here, this is my second way of doing an elimination. What do you think the product of this is going to be? That's the only possible product. All right. Let's talk about this one really quickly. Why is this the answer? Anyone has an explanation for why this is the way it is? I formed the same carbon cation, right? Well, to be honest, there's no carbon cation that forms here, all right? So this is an E2 mechanism. So all that you end up doing is making that a good leaving group, right? But it doesn't leave, it stays on. And you have to pull a proton from the neighboring position to kick off your leaving group, right? So let's kind of draw that out really quickly. I know that's confusing. You guys haven't seen this chemistry. But basically, you end up forming something like this. Okay. So you end up making this very reactive oxygen species. Again, this is an oxygen that has a plus charge. It has the P with a double bond to an O and 2 chlorines. You're actually going to lose one of the chlorines here. All right. And this is just like any typical leaving group. But in this case here, there's no driving force to knock this off. So what does that mean? I can't just, this doesn't leave like a great leaving group like water. Water can leave because of heat, right? When you heat something, you form steam. You think this is forming steam? No, it's not. So if you heat that, it still stays together, right? So this is just a leaving group. I just put a leaving group on a molecule, right? However, if I have a base present, what can I do if I have a base and I have a leaving group on my molecule? So a base doesn't mind doing what? Eliminations, right? Nucleophiles do what with leaving groups? Substitution, right? So if I have a nucleophile, I would substitute. But if I have a base, I would just do what? Elimination, right? Good. So do I have a base in solution? What did I do, right? This thing here, right? This trialphaamine is a very good base. So the lone pairs here are going to grab. I didn't want to do the mechanism, but I ended up doing it anyway. Guess it's okay. These lone pairs all right, those lone pairs are going to grab that proton and the corresponding electrons in this bond here are going to form a double bond, and I'm going to kick off my leaving group. Right, give me a second. I did not plan to do all this today. But I think this helps, right? Hopefully. Not as bad as you think. Trust me. Not as bad as you think. So the good thing is, if you see me making mechanisms, you can draw these same mechanisms where in your notes, right? If I'm doing them live, you can do them live too. It's different when I have them already made in the PowerPoint presentation. But if I'm drawing them live, I want you guys to really know these, right? To be comfortable with these mechanisms. All right, so once I've removed the proton and broke this bond, right? I'm going to form this alkene plus my byproduct. Which is this PO2 CO2 compound. Yep. Yep. Actually, let me do it the way that you guys are comfortable with it. All right. You guys are more comfortable seeing that go to oxygen. It doesn't matter. So oxygen and phosphorus bonds are really favorable. We'll talk about that a little bit later in the semester. So really, this bond is actually going to form a double bond with the phosphorus. But for now, let's not do that. I'm sorry, you guys don't know that yet.
Can you explain what happened to the 3 on the net when it bonded with the hydrogen?
Yeah, it's still there. I just haven't. I forgot to put it in. I'm sorry. There's still 3 alpha groups on that. Okay, we got it together now. All right, so phosphorus oxide tetrachloride substrate is just going to convert the OH into a extremely good leaving group. Right, it's just going to attach itself to O, and now O becomes very easy to leave. However, it cannot leave under heat. All right, so just sitting there until a reagent promotes something else. In this case here, we have a base that's ready now to pull on the protons, all right? And conveniently, there's only these protons that can be removed, right? Next door up here, are there any protons in that carbon? With the dimethyl group there, is there any hydrogens there? Or any protons? There's none, right? So this is the only position that can remove protons to form a double bond, all right? So I just grab one of those H's, the corresponding electrons form a pi bond while I kick off my leaving group. That gives me my final product, which is my alkene now with all of this inorganic byproducts. Okay, good. As long as you can work with the acid versions and think about rearrangements if they're going to happen, and you can think about these as a regular E2 mechanism, you're going to be doing well with all the potential dehydration processes that can happen with alcohols. Okay, good. Let's keep working on other reactions. This is the class of reactions I wanted to get into. Give myself some more room here. All right, class 2, we're going to call reactions at O, right? There's three main reactions at O. First is it, I don't know if it's called, we don't call it ether formation. We can't really, the other word is esterification. This is just ether formation. All right, so what does that look like? I'm gonna take a regular alcohol. And I'm going to introduce it to base here. Most people like to use sodium hydride, I'm sorry. And I'm going to introduce it to RX. Is everybody cool with RX? What does X stand for again? Any halogen. Very good. And this is going to create an O R compound. And that functional group is known as a what?
Is it an ether?
That's an ether.
Ether.
That's right. So here I form my ether. All right, let's do a real life example. I'm going to go back to that same molecule that I've been using earlier.
And Dr. Cooper, you said the R stands for what?
R stands for any hydrocarbon. Yeah, maybe I should put that note here.
So the halogen will be made into a byproduct now?
Yes, if you want to look at the byproduct, it's just going to be, you're going to form hydrogen gas here. Plus sodium X. So maybe I should put that in red. Okay, good questions, good question. Yeah, those are the byproducts. I'm not extremely interested in those, but it's good to see that if that's how you like to think about things, which is good. People that are concerned with all products are engineers. So you guys should think about chemical engineering, right? They think about mass transfer and all that because they have to deal with the waste that generates in the flask. But most of us that works at the small scale, we're not all that interested. So I'm going to use my strong base here, which is sodium hydride. And that first step is just a deprotonation step. So maybe I'll do the mechanism here shortly. I know I'm short on time, but I think I can get the rest in as well. I want to finish all 3 of these today. And then I want to talk about the other reactions, which is redox chemistry, and then we'll be good for today. All right. And for my alkyl halide here, I'm going to use just a simple molecule. I'll use this molecule here. All right, so let's do the mechanism really quickly. All right, step one, this are from the first step, what is called step one. This is called deprotonation. What does that mean? Yeah, what does deprotonation mean? What does that really mean? Okay, could be. Anybody else? Any other
Is
take?
it removing a proton?
Yeah, removing the proton. Where we remove? What proton are we removing? You think?
The one near the OH?
Yep, the one at the OH. So maybe I should just draw like this. First thing that's going to happen, I'm going to put plus sodium and H. And what type of bond is between sodium and that hydrogen? What will you guys tell me? Sodium is a metal and hydrogen is a non-metal. So what type of bond there? That's ionic.
Ionic?
Very good. Very, very good. So I'm going to draw it as its true ionic state. If I can here. The computer's giving me some issues. So a hydride is what? It's a hydrogen atom with 2 electrons, right? And a form of what charge? Negative charge, right? It's tripping, but we're going to get it together. All right. So because I have lone pairs here, I could be either a base or a nucleophile. And in this case, I'm going to be not a nucleophile, unfortunately, but a base, right? Because base likes to do what to protons?
Eliminate.
Yeah, they like to eliminate, or another way to say is that they accept protons, right? Acid donates, but a base will accept those protons, right? So I'm going to accept a proton. So I'm going to attack that H. Just the H, not the electrons in the bond. All right. Let's get an arrow here at the end. Let's call that red. All right. So what happens to the electrons that were shared to the H? What do you think happens? They're going to break and reside solely on, oh boy, here we go. Backing up. All right. Solely on that O. Is everybody comfortable with that stuff? Yep. Say that one time. No, no, no. It's not doing nucleophilic attack. It's just removing the proton. So because I have lone pairs, I could be a nucleophile or a base. But in this case, because the word is deprotonation, I know I'm accepting a proton. So to accept a proton means I'm a base. That's the definition of a base, to accept a proton. So all I'm trying to do is grab this H. All right, so maybe I should color that a different color, keep track of it. So hydride H that has a lone pair on it is going to attack the H. So I just show an arrow going to H, right? And I'm saying I just went to H. But this arrow that goes to H does not explain what happens to the electrons. And this is where we want to make sure undergraduates are thinking fully about is that to complete this mechanism, you have to show what happens to all things related to the H. Sorry, the computer is not recognizing that negative charge is on the H. Still not recognizing it. It's okay. So to remove fully the H, we have to deal with the bond that's also present there. Are you guys comfortable with that? So when you show a mechanism, and I said that I'm deprotonating and I'm dealing with this H, I have to make sure I still do something with this bond there, right? This showing the arrow to H doesn't break it yet, right? It just says that is going to donate electrons in. But I have to show that now this bond that has 2 electrons are going to break to give electrons to oxygen. So when I draw my product, what would I have? Come on, come on. Sorry, this is me, like, getting frustrated. What in the world, really? I'm gonna lose this whole document. I can't afford to lose this today. Please, please. What's the product? I'm trying to draw the product out. Sorry, if you're in Teams, my computer just went down. Give me a sec. I'm hoping that it will recover. While you guys are waiting on me, could you draw the product from the depronation? What will I form? Not a double bond. This is good. This is a good question. So this helps me think about how to teach this as well. I want to see how you guys think about these arrows. When I see these arrows, what are they trying to draw? What are the products that come from it? So think about it. If I'm saying the 2 electrons from H, and think about hydrogen as having some location that can receive those electrons, right? So that H that's bonded to the O, right, is going to make a new bond with that H, right? That's what it's saying. So these 2 H's now are going to connect to each other, right? And I used to be connected to O, but I broke that bond and gave 2 electrons back to O, right? So how does that look as 2 new products? Computer, come on, come on. Teams, are you guys still with me? Can y'all still hear me? Oh, I lost Teams.
No, we're still here.
Okay, I thought I lost Teams too.
Yeah.
I was like, dang, I lost everyone. Kim Draw, why are you doing like this today?
So I explain like everything from beginning to where we at now. And I think I'm using, I just got to use it again where we took the long period on the A's.
Okay, yeah. So all I'm doing is trying to depronate, right? And H, lone pair. So I'm accepting a proton, that's right. So depronate, I'm accepting a proton from somewhere. And so this H is accepting that proton from the alcohol, right? And in doing so, I'm going to break the bond between O and H. All right, I got my screen. I got another window. Teams, can you guys see this one?
Yes.
Yeah.
Okay, great. Very good. Let's try this again. All right, give me 1 sec. I'm going to change the settings. That's probably why this thing is breaking. But this is my favorite set of settings to teach it. And I also wanted to say this to you guys as well. I do have office hours, so if there's anything that's going on in class that you guys want to talk to me in office hours, please feel free. We have virtual office hours and things of that, so I'm hoping that we can work things out. All right, I'm going to change the mechanism a little bit here because of time, but it's exactly the same thing. I want you guys to get comfortable with that in your mind. I'm going to start at this electrons here. Okay, here we go. Now this is acting weird. All right, that's not going to do what I wanted to do. So what am I doing right here when I'm showing this stuff? Okay, good. So this is saying that the electrons that are between the sodium and the H, these electrons are being used to donate into this H, right? Right. And so when electrons are donating into an atom, what am I doing? I'm asking these questions. I'm hoping this helps when you guys think about mechanism. But what is that really trying to?
Is that pronation?
It's not pronation in the sense. I guess I know it's tough. You can kind of think about it as pronation because it is an H donating into another H. But can you guys give me something similar? I'm sorry, not similar, but something simple, a simple word or something, not a high drive shift, something even simpler than that. What is that arrow, that first arrow really trying to showcase? I guess you can say a hydrogen bond. That's, you can think about sharing electrons maybe. Oh, okay. All I'm really, what I was looking for you guys to say is that I'm making a bond. So this is showing that a bond is being made between, so maybe I'll do this differently. Maybe I should do H bonded to H. So that first step is showing that the H in purple and the H in red have made a bond, right? Then what has happened? Also, all right, good. So I have a organic molecule now that does not have an H anymore. I'll draw the lone pairs and it gained a new lone pair. So keep in mind that this molecule had 2 lone pairs. And this one has now 6 lone pairs, right? Start off with 4. So I'm put this in red. That's a lone pair that got gained. This is why now this is a formal negative charge. And I have right next to it a sodium that has a positive charge. Okay, are you guys comfortable with that stuff? Hopefully you are. All right, and this is step 1, which is deprotonation. Right? This compound that has a negative charged oxygen species is called an alkoxide. It's like you guys know sodium hydroxide, we use the word alkox. This stands for alkyl group, oxide, right? So this is an alkoxide. So I might use that word in the future. You guys know what that means now. I said forming the hydroxide or the alkoxide. All right, step 2 of this process now is a plain O alkylation, which is just an SN2 reaction. So now my alkoxide, which is formed in this reaction, I can't remember what I used earlier. I think I used maybe 4 carbons bromide. Was it 4 carbons? You guys have your notes? 1, 2, 3, 4. Or was it 3 carbons?
3.
It was 3 carbons? Okay. All right, so I'm going to react now with propyl bromide. What happens here? Where's my nucleophile? Some lone pair on the alkoxide, right? Yep. Here, I'm going to attack that carbon. And my leaving group is going to leave, right? Oh, come on here. So in doing that, I get what now? my final product, which is this compound here, which is known as my ether. Okay, so that's a lot of work, somewhat. You don't have to do all that. Hopefully, you can start to think about this in your mind. Yes, ma'am. Okay, we'll do. Give me one sec. So someone asked me to explain this. I wanted to just showcase again the overall reaction, which is sodium hydride with that propylbromide. That looks so weird to me. Okay. So that's the ether step there. Overall, there's 2 steps. So let's talk about this. I didn't draw the byproduct, so maybe that would help if I do that. We get this sodium over here. Right. Does that help? That's what you're looking for, the sodium bromide. So all that happens here in the second step is this alkylation is that lone pairs on O attack that carbon that has a leaving group, right? So now I make a new bond between oxygen and carbon, and the electrons in that bond break to exclusively go to bromine. So now I have a sodium and a bromine that are attracted to each other. On the oxygens, you don't, but in the mechanism, either you have to start your arrow from a lone pair or from the minus charge. So you don't have to show lone pairs, but your arrow has to start from the lone pair if you draw it in, or from that minus charge. Okay. The minus charge is the same as letting me know that you're seeing electrons on O. Any questions overall with the ether formation? Any questions on teams? All right, no questions. I need to finish up really quickly. I'm not going to give the mechanisms, but I'm going to introduce the next type of reactions. Right, and you guys will be done for the day. All right, the next type, this is still reactions at O, is an O totylation. Total group. All right, is this molecule here? This is toluene sulfonyl chloride. I'm gonna do, I'll talk about this more on Thursday. I just want to show the group now. So I can take any regular alcohol, which here again. All right, and this is typically abbreviated as TSCl. Okay. And I can react it with topsyl chloride. And step 2 is some very mild base. I'm just going to make it generic. We need some base to just generate. There's going to be a little bit of acid, like HCl, that forms. We need to make sure that we soak that up with something. And that's going to convert this alcohol into an OTS. Which is another way of saying if we draw the full compound out, it will look like this. All right, most people do not draw the tosyl group out, which is, that's why we use that abbreviation of the TS. But I know this is your guys' first time seeing it. They give me my brackets here. All right, and that part of the molecule is the tosyl part, right? I'll put this in red here. Put this in that pink. So this is a tosylate. All right, what's the advantage of tosylates? Tosylates are an extremely good leaving group. So most people make tosylates because they want to make that oxygen leave in some type of next step chemistry. So this is a great way to make that oxygen TS leave in some type of process. All right. That's going to be a reaction that comes up that we need to make the tosyl first before we do the next step. Yes, this is actually better than water, but it's in the, I'll say it's in the same range. Whenever you put a plus in oxygen, it's a great leaving group. This is a nice, convenient way to do this without having to introduce that strong acid. So you can make the tosyl. All right. Also, there's something called O esterification. All right, I'm going to make an ester. So I'm just going to copy this. So I'm going to take my alcohol and introduce it to some type of alcohol. I'm sorry, carboxylic acid derivative. And typically you would need acid here to do this. So I'm going to say H plus as well. Okay. And that's going to convert this compound into a this functional group here, which is known as an ester. All right, we'll talk about the mechanism a little bit later here on this, but this is a classic way of converting an alcohol into a tosylate. So let's kind of review these three processes, right? I didn't talk about it up here. This is ether. Say that one more time. No, talk about down here. No, that was just a teaching strategy. I want you guys to see that this was the TS part of OTS. So let me, good question. You don't need the brackets. I'm just trying to use it as a teaching strategy. Okay, so O ether. Again, these are all reactions at what part of the alcohol? The O. I'll say it one more time, hope that this settles in. So you guys just learned that an alcohol can dehydrate, right? So that means I can lose water from alcohol. And if I ever lose water, I'm going to form an alkene. So that's the first reaction you guys want to have in your brain. Alcohols can dehydrate. Alcohols also can react at the oxygen. So everybody's getting comfortable there now, right? So what are the different ways I can react at the oxygen of alcohol? I can convert the H into an R, right? And if I convert the H into the R, I made a what functional group? An ether. All right, so that's my first class of reaction is O ether, all right? Reaction at the O. The second reaction I can learn that happens at the O of an alcohol, instead of being OH, I could be O what now? Tosyl, right? So I can be OTS. So keep that in mind. Maybe I should go back here. I got some weird looks in class. It gave me the mindset to try to go back and work on this. I'm out of time too. I'll put it in the new set of notes that I'll send you guys. But I can go from OH to OA. OR. That blue. All right, and this is an ether formation. I can go from OH to OTS, that's O tosylation, and I can go from OH to O double C double bond OR, right? This carbonyl containing group, and that's O esterification, right? So the next class of reactions to alcohols you guys are learning are reactions at that oxygen, right? Where I substitute the H for something else. Okay, good. I thought it had multiple pages here. All right, I'm going to end here because I'm really getting dangerous of time. I know you guys have other classes. Keep in mind, there's two other processes that we need to learn, which is O substitution. So we're going to convert the whole OH into an X. And what does X stand for again? Any halogen. So I can convert an ROH into RCl or RBr or RI, right? That's called substitution. Any halogen, anything in group 17? You got something in class? Oh, yeah, you gotta run. Go ahead. You gotta run. I completely understand. See you guys. All right, substitution is going ROH to RX. And that could be either any halogen, a bromine, a chlorine, an iodine, or fluorine. And the last thing that we need to learn with alcohols is redox chemistry. Oxidizing an OH into a ketone, an aldehyde, or a carboxylic acid. And then we're going to talk about, yes, ma'am? Which one? This right here? Oh, there's nothing behind the H. Sorry. Oh, you mean this H? Yes, that's acid. I'm so sorry. Yes, H plus. You need a little bit of acid to catalyze that reaction. All right, and the last thing is redox chemistry, where you can oxidize and reduce. And then we'll talk about a new way to make alcohols. And then we need to summarize from double bonds and triple bonds and from alkyl halides, how do we make alcohols? Yeah, it should be in teams. If you log into teams, I have the role. All right, see you guys Thursday. I'm gonna stop the recording now. I apologize. I'm gonna send you guys some notes. Stop recording.